Hello, and welcome to today's ACM Learning Webinar. This webcast is part of ACM's commitment to lifelong learning. This webinar is brought to you by the Special Interest Group for Artificial Intelligence, known as SIGAI, and specifically the SIGAI Industry Committee. We're planning to have monthly webinars on different topics of interest for those in industry and academics as well. I'm Rose Paradis, Secretary-Treasurer for SIGAI, and I'm also a member of the SIGAI Industry Liaison Committee. I am a principal researcher for Leidos, where I work as a data scientist and do big data analytics. My work focuses on computational linguistic and natural language processing, as well as machine learning. Plamen Petrov, the Industry Liaison Officer for SIGAI, is not able to be here today. Today's presentation is Artificial Intelligence with Bayesian Networks, Data Mining, Knowledge Modeling, and Causal Analysis by Lionel Jouffe. You can also find more on our backgrounds in the bio widget on your screen, but I want to go over a few things and I'll do more of an introduction in a second. I'd like to talk a little bit about the ACM and SIGAI. For those of you who may be unfamiliar with ACM or SIGAI, ACM does offer educational and professional development resources that can bolster your skills and enhance your career opportunities. Our members stay competitive in the constant changing world of computing with a range of ACM Learning Center resources, which you can see at the learning.acm.org. You can see some of the highlights on your screen. And the Special Interest Group on Artificial Intelligence, which is presenting this presentation today, is made up of academics and industry researchers, practitioners and software developers, and users and students. Our main goal is to promote and support the growth and application of AI principles and techniques throughout computing. We also sponsor or co-sponsor high-quality AI-related conferences. We also publish our quarterly newsletter, AI Matters, and that's available, you can see in some of the links that are going to be coming up at the end of this presentation. There's a few more things we do that are listed here, as well as you can go to our online links on Google, and both members and non-members are welcome to join our mailing list to receive any announcements of interest to researchers and practitioners. The next thing I just wanted to do was to go over some housekeeping items before we get started. First, the slides will advance automatically throughout the event. You'll see the slides as well as that I'm presenting, as well as the slides that Lionel will be presenting. If you are experiencing any problems with the slides or audio, press the F5 key in Windows, Command+R if you're on a Mac, or refresh your browser on a mobile device. Or you can close and relaunch the presentation if all else doesn't work. To control the volume, you can adjust the master volume on your computer. If you have any questions during the webinar, please type them into the Q&A box at any time during the webinar and click Submit button. I'll organize the questions as Lionel speaks, and he's going to reserve time at the end of the presentation to address them. So feel free to put any questions in that you may have. This session is being recorded and will be archived. You will receive an automatic email notification when it becomes available. And you can check learning.acm.org for updates on this and other upcoming webcasts. At the end, a short survey will be taken. By going at the end, it'll pop up, or you can see it by going into resources. Today's presentation, as I mentioned before, is Artificial Intelligence with Bayesian Networks, Data Mining, Knowledge Modeling, and Causal Analysis by Lionel Jouffe. Dr. Jouffe is co-founder and CEO of the France-based Bayesian SAS. Lionel holds a PhD in computer science from the University of Bonn and has been working in the field of AI since early in the 1990s. While working as a professor researcher at ESIEA, Lionel started exploring the potential of Bayesian networks. And after co-founding Bayesian in 2001, he and his team have been working on full-time development of the Bayesian lab. which has since emerged as the leading software package for knowledge discovery, data mining, and knowledge modeling using Bayesian networks. The usual lab enjoys broad acceptance in academic communities as well as in business and industry. If you cannot see these slides that Lionel will be presenting, please hit the slides in the resource list. And Lionel, without further ado, I'd like you to take it away.
Okay, thank you, Rose. First of all, perhaps I'm going to wish you a happy New Year to you all, and then I'm going to start this presentation that should last 40 or 45 minutes. So thanks for joining this webinar. And so I'm going to talk about how to use Bayesian networks for data mining, knowledge modeling, and a little bit of causal analysis, right? But before, I'm just going to say a few words about our company because we are a small French company. So this is a company I've created with my co-founder, Dr. Paul Monteanu, in 2001. We are based in France, in Laval, more specifically, near Paris. We are 7 in France, but we also have Bayesian in the US since 2010, and also Bayesian in Singapore for the Asian market. And even though we are pretty small, we also have a worldwide strategic partnership with P&G and Procter & Gamble and some reseller and partners. Here is just a subset of the customer we have. So we have more than 700 customers, and this is ranging from academic customers to also, governmental agencies, market research agency, communication, banks, energy, transportation, the U.S. Army, and some also small customer as Microsoft, Intel, and things like that, right? So now the question is, why do these customers and why do we need to use Bayesian networks? The idea is to try to help Stu. So I don't know if you are familiar with Stu. This is this green guy. And every day we have to take decisions under uncertainty, right? So this is quite difficult. We have lots of drivers that are available. And as human beings, if we have more than 3 or 4 connections between these drivers, this is over. So we will oversimplify in order to take our decision, right? So the idea of using a Bayesian network is to build a model, a graphical model of the world that is behind these drivers, and that will explain the connection between these drivers, right? So we are going to create this kind of model and then use this model for reasoning and inducing the optimal policy in order to help Stu, right, and make Stu happy. So this is the objective of using Bayesian networks. So at the end of the day, we are looking for what we call a probabilistic expert system. And a probabilistic expert system, this is a system, a computer program that will help us to do reasoning, automatic reasoning, right? And when I say reasoning, I mean that we do have some insights, some sensors or information about the real world, and we want to use this information in order to reach conclusion on the dimension we cannot observe, or for which we don't have any information yet, right? So it can be for diagnosis, for speech recognition, and for driver's analysis, something like that. So what we were doing in the late 80s was to design, specific programs for solving the problem, and these programs were based on expert rules, so usually deterministic rules, and the idea was to design this program in order to mimic the way the experts were reasoning, right? So we were just trying to do the same thing as what they were doing, but at the end of the day, it was probably not the best idea. So a much more modern approach consists in, instead of trying to mimic the way the experts are thinking, we are going to use their knowledge in order to build or learn a Bayesian network, a model that will be then used for reasoning. And then by using this model, we are going to create automatically or induce the optimal policies. So this is the idea. So we are clearly in the world of modeling, right? So I guess that everybody knows what is a model, but I'm just going to use some example. So this is a simplified representation of some aspect of the world we are analyzing. And it can be something very simple. It can just be a drawing, right? So it can be a 2D drawing. So here, as I'm French, as you can see with my accent, I have a model of Paris. So it's just a basic drawing, but it's already enough for communication. For example, I can use this drawing in order to describe that we did our Bayesian conference in September in Paris. It was very close to the Eiffel Tower, and then we had a cruise on the same river. We were close to Notre Dame and so on. So it's enough. I can already use that for people who don't know Paris. It will be enough, right? I can also add a third dimension. So this way I will be able to see that the Eiffel Tower is quite high, but otherwise the building in Paris, we don't have any skyscrapers here, right? Except a few in La Défense, right? And it can be something like a skeleton, right? So this way you can do some reasoning about the bones, about the muscles. It can be something like that for reasoning about the solar system, so very simplified one, but this will give you the relationship between the planets. It can be something more complex, like a set of mathematical equations in order to represent the dynamics of a bicycle. And what we are going to use is a model based on a graph. So this is a Bayesian networks where we have the nodes represent the dimension of the domain we are analyzing, and the connection between these nodes represents the probabilistic relationship between these dimensions. So this is the kind of model we are using. And in order to have a very useful model, we need to be able, or our expert system need to be able to manage uncertainty, right? Because uncertainty can come from different sources. It can be because you have partial observations. You don't see everything, right? So then this will introduce uncertainty. Or even though you are measuring everything, usually you have noisy information. Your sensors are not perfect, so because of the noise, you will have uncertainty. Or it's just because you have an incomplete knowledge. So you don't even know that you have to measure a dimension. So this way, you will have uncertainty. Or it can be something that is absolutely by definition not deterministic, right? So even though from a philosophical point of view, you can always think about perhaps this is because you have an incomplete knowledge, but I think this is another debate, right? So because of this uncertainty, right, our expert system should be able to consider all the possibilities. And for illustrating this purpose, I'm going to use a medical example. This is usually what we are using. So let's assume that I'm observing some symptoms. I will see that lots of diseases can have triggered these symptoms. So if my expert system just gives me the list of the diseases, it will not be very useful. So I need to have something useful. I need to have an expert system that will go beyond that and give me an ordering, right? And start with the most likely disease. And this is where we are going to use probabilities, right? And for dealing with probabilities, right now the best way to have a compact representation of what we call the joint probability distribution of a domain, it's to use a Bayesian network, which is a kind of zip of compression methods for building these or representing this joint probability distribution. So a Bayesian network is a compact representation of the joint probability distribution, and it is done via a graph. We are using a graph, so this is something that is nice because you don't need any PhD in statistics to understand the graph, right? So if this is your domain, you will understand what are the nodes, you will understand what are the connections, and then you can challenge this model. You can audit this model, right? So this is not a black box. And then because you can understand it, you can also use your expert knowledge to directly create this graph by using your expert knowledge. And if you have data, you can also machine learn the Bayesian network. So you can do at the same time knowledge modeling and machine learning. And once you have your model, then you can use this Bayesian network for probabilistic reasoning, and you can then implement what we call the plausible inference. So here just a few words about black boxes and crystal boxes, because we are talking, when we talk about now artificial intelligence, lots of people are thinking that there is only deep learning, because this is what we are listening every day. So deep learning, so this is very efficient, but at the end of the day, this is more or less a black box. So you have a neural network that is approximating a function. So you have input, you have output, but in the middle, it's quite difficult to understand what happens. So you have weights and so on, but this is not easy, right? And on the other side, the Bayesian network is absolutely a crystal box, right? Because as I said, this is a graph, so you see the graph, you see the node, you see the connection, and you can really audit this graph just by looking at the structure. So you have already, just by looking at the graph, you have a qualitative information about your model, right? So this is very, very different from deep learning. So now just a few words about what is a Bayesian network. So as the name indicates, this is coming from the Bayes theorem, or at least this is implementing the Bayes theorem. This theorem is quite old. This is 1763. And this is a theorem that allows you to compute conditional probability or posterior probabilities. So I'm going to use here again the example of the medical application. So here, let's suppose that H stands for hypothesis. So this is a list of the diseases, right, if you want. And B stands for the data, so what you are observing. So these will be the symptoms in our case. So you are observing symptoms and you want to compute probabilities for all the diseases, right? And these probabilities will be indeed proportional to the prior. So what is the probability of the disease if you don't know anything? So the marginal probability. And then the likelihood that the disease has generated the symptoms, the data here in that case, right? So this is just the product between these two terms. And this Bayesian network, or this Bayes theorem, is represented by these Bayesian networks where we just have two nodes, one for representing the disease and one node for representing the symptoms, right? And we have a link. So in that example, this is a causal link from the disease to the symptoms, right? So it's a very simple network. So now I'm going to talk a little bit about cognitive science, because in this community, since a few years, they are starting to use or to analyze Bayesian network, because it seems that we have a probabilistic brain and that Bayesian networks are a very good candidate to represent the way we are thinking. And I'm going to use this example. So unfortunately, I cannot have any feedback with you guys, but I have a few colleagues here in the room, so I'm going to use them. So here, let's suppose this is Jean. You can see Jean here, and he's coughing, right? And I want you to take into account three hypotheses, right? So the first one, Jean is just suffering from a cold. The second one, unfortunately, he has a lung cancer. And the third one, he just has a heartburn, right? So the information you have is you just see Jean coughing, right? And I want you to give me what is the most likely explanation for this coughing. So I guess that most of you will say, well, this is cold, right? So even though the other ones are not impossible, this is probably, you just have a cold, right? So in order to reach this conclusion, what you have done is just you have implemented the Bayes theorem, even without knowing it, right? So because here what you did was just to compute what is, or to estimate what is the prior to have a cold, what is the prior to have a lung cancer, and what is the prior to have heartburn. And in that case, the probability to have cold and heartburn is much higher than a lung cancer. So you will favor cold and heartburn. And then you have also weighted this by the likelihood. So given that you have a cold, what is the probability to cough? Given that you have a heartburn, what is the probability to cough, right? And in that case, this will favor, again, cold and now lung cancer, right? So at the end of the day, mixing the prior and the likelihood, the winner is cold, right? So this is here the Bayesian network that represents this very simple problem. So I've designed here a fourth hypothesis where you don't have anything, right? And then 21% of chance to have a cold, 1% of chance to have a cancer, and 7.5% of heartburn. Then there is a causal link to coughing. And then what we do with these Bayesian networks, we are just observing that coughing is true, and this is using the system to backpropagate and compute, update the probability of the diseases, right? And we can see that cold is indeed the most likely disease, right? So this is indeed what you have done without thinking about it. Now I'm going to use a second example, because if you remember what I said a few minutes ago about uncertainty, when you are not observing all the dimensions, then you have uncertainty. And here, with images, we usually miss one dimension because this is a 2D representation of something that has 3 dimensions. So in this image, let's say that we have 2 types of objects. Right? So we have, let's say, a concave and convex object, or bubbles and holes, if you will. So when you look at this picture, I'm pretty sure that most of you see 5 bubbles and 1 hole, right? So 1 concave object, right? So now I'm going to use the exact same image, but in the other direction, right? And now I'm pretty sure that you see 5 holes and 1 bubble, right? So right now, nothing surprising, but now I'm going to again use this same image, but vertically. And here this is much more challenging because you can look at this image and perhaps you see 5 holes, or 6, or 2, or 1. And indeed, you can look at this image during 10 minutes. It will keep changing. You just have to blink, and then this will change, right? So I don't have any feedback, but I'm pretty sure this is what you see, right? And here, in order to explain that, this is the Bayesian network that represents the way we are perceiving this image. So we are first taking into account where is the light coming from, right? Then we are taking into account where is the shadow, and this, by using these 2 components simultaneously, we are inferring if it's a bubble or if it's a hole, right? So as human beings, usually the light is coming from the top, right? So we have a much higher probability for the light coming from the top. From right or left, let's say that this is more or less uniform, and the probability that the light is coming from the bottom is very small, right? We don't have any prior for the shadow, and then if we don't have any insight, we don't have any prior for bubble and holes here. So in the first example, the light is still, so the probability for the light coming from the top is high. We see that the shadow is at the bottom, then we will naturally infer that the object is convex, so it's a bubble, right? In the second example, the shadow is at the top, right? So in that case, given the likelihood or the distribution for the light, we will naturally infer that the object is concave, that this is a hole, right? But when the object is like that, the shadow is on the left, so the Bayesian network will give us a uniform distribution for concave and convex, right? So with this model, we know that this is uniform, but the problem is that our brain has to take a decision. So you cannot just say it's uniform. So we have to decide if it's a hole or if it's a bubble. And this is the reason why you can look at this picture again during 10 minutes, and it seems that our brain is indeed sampling in the joint probability distribution. So if you measure how many times you see a bubble and how many times you see a hole, you should be able to build back the distribution, right? So I think this is quite interesting. So, as I said, so it seems that we do have a Bayesian engine in our brain, right? And that we can represent this engine by using a Bayesian network. So the thing is that our engine is very efficient, but only when we don't have to think about it. If we have to do some kind of computation, probabilistic computation, then we are really, really bad because we have lots of biases here. So the main idea will be to use our expert knowledge in order to build these Bayesian networks, right? In order to represent the way we are thinking, because we know we can do that, right? And then we're going to use this model for computing, for doing exact inference, right? So this is exactly the same thing as computing or programming a calculator, right? For doing complex computation instead of just trying to do that mentally, right? So now that we have seen the power of these Bayesian networks, we always have to think about when we build a model, what is the reason for this model? What is the purpose of this model, right? Are we going to use this model for prediction, or are we going to use it for explanation? So for prediction, this is indeed one example is to build a Bayesian network to compute what is the probability that a customer will be interested by a new product, for example. So this is a typical example of prediction. And for explanation, this will be for, I want to use my model, but in order to find what are the optimal drivers for increasing the sales, right? And this is very, very different because, for example, if I want to predict the size of a company, I can, for example, use the number of cars in the parking lot, right? So I guess it will be a good indication of the number of employees in the company. But if I want to increase the size of Bayesian, it's not as easy as just adding car in the parking lot, right? So it's not a driver per se. So it's good for prediction, but it's not good for optimization and explanation, right? So this is really the big difference between these two approaches. And the second question you have to think about is, what are you going to use for building this model, right? How are we going to build this model? And the thing is, here I'm using this image just to illustrate that we are working in a domain, and here you have particles, and each particle is indeed one observation coming from this domain, right? So in this domain, either you have something that, sensor, surveys, experiments that will allow you to, given these particles, to build a structured data set, and then you will be able to use machine learning, or you are not so fortunate and you have unstructured data, and this unstructured data will be stored as explicit and tacit expert knowledge. So you will have people that will be trained, that will go to conferences, that will talk with their peers, that will do some kind of experiment, and everything is unstructured, but they have experience, right? And this data, these observations are then stored as an explicit and tacit knowledge. So we have then two ways. So either we are using this knowledge or the structured data set. So given that we have these two sources of knowledge, so we can create a mapping. So this slide here is indeed a kind of meta model. So this is the same thing as the map of Paris. So it's a two-dimensional model of something that is much more complex. So obviously, as all the model, it's wrong, but it's still useful for me for explaining what I want to explain. So we have two axes. The x-axis, this is a purpose. Are we going to use a model for just association or prediction, if you want? Or are we going to use it for optimization? And then here on the y-axis, this is the source. So at the very bottom, we are going to use the expert knowledge, and here we are going to use the data, right? And there are two main quadrants in this map. The first one is Q2, so this is where you have all the big data stuff, deep learning, scoring, and so on. And here, this is where you have something for where you are using causal analysis, something like that, right? So the good point with the Bayesian network, the Bayesian network framework, is that it allows you to cover this entire x-axis. So you can use Bayesian networks for machine learning, for just prediction, right, for discovering association, and you can also introduce some kind of causal assumption for doing optimization, simulation, and explanation. And you can also cover the entire y-axis, which means that if you don't have data, again, you can use the expert knowledge to build your model, and the more data you have, the more easily you will be able to do machine learning and create automatically your model, right? So this is really something important, and I guess this is the reason why Judea Pearl, the father of Bayesian Network, received the ACM Turing Award in 2012 for its contribution that changed the field of artificial intelligence, which is indeed the equivalent of a Nobel Prize for computer scientists, right? So now I'm going to use an example, just a very basic example of Bayesian networks coming from Q4, if you will. So where we have an expert, and this guy is about to retire, so you have seen lots of particles, if I'm using the image I had before, and it's not structured, right? So it's just his experience during 40 years, and he's a specialist of lung disease, and it's very simple model, where we have three diseases, so bronchitis, cancer, and tuberculosis. We need to have information about the patient, so we have age, smoker, and dyslipidemia. and two symptoms, very simple one, dyspnea, so this is a difficulties to breathe, and X-ray. So if we carry out an X-ray, are we going to have a abnormal or normal result? So given this, here is the network this doctor has designed. So we have one node per dimension. So we have one node for indicating if the patient went recently or not to Asia. We have a node for age, a node for smoker. Then we have in red the three diseases, and then the two symptoms. Plus here an artifact, just a node we have added in order to simplify the graph, but I don't really have the time to explain that right now. So here in this graph, you have these nodes, and you also have links, right? So that indicates a direct probabilistic relationship, and sometimes this relationship is causal, and in that example, this is the case, right? So as I said before, you don't need to have a PhD in statistics to understand this graph. So if you are familiar with this domain, you can see that age have a connection with smokers, so you can imagine that the younger you are, the most likely you are a smoker. A smoker has a link with bronchitis, so you can guess that if you are a smoker, you will increase the chance to have bronchitis. Bronchitis has a connection with dyspnea. This is probably because this will increase the probability to have dyspnea. So even though you cannot directly read that on this qualitative structure, if you have some expert knowledge, you can quickly understand this graph, right? So this is just the qualitative part, and from the quantitative part, we have parameters associated with the nodes. So, for example, age, it has three states. We have some young adults, adult or senior, and we have to define a probability distribution. What is the probability to be a young adult when you go visit this doctor? What is the probability to be an adult or a senior? And this probability can be just completed by using the expert knowledge of this doctor. Or you can use brainstorming and use a group of experts in order to reduce mistakes and reduce the biases, right? Or if you have a structured data set, you can also use a kind of frequentist approach, just count how many adults, young adults, and so on, right? So we have these three possibilities for populating these tables. Then when we have incoming links in these nodes, and now I'm going to focus on cancer, this node has two parents, so we need to quantify this relationship, right? So here we have a table where we have to define what is the probability when you are a smoker and a young adult to have cancer. So here it's 1%. If you are a smoker and adult, it's 5%. If you are a smoker senior, 15%. So the risk of cancer is increasing from 1 to 15 when you are a smoker, given your age. And then same thing. For no, you are going to describe for non-smoker, young adult, 0.1, adult 1, senior 5. So the risk is also increasing, but it's lower, right? So you have to define all these conditional probabilities. And now let's imagine that you have probabilities associated with all these nodes. Then we have a compact representation of this domain, right, of this joint probability distribution. And we can use this model as an expert system. So now let's imagine that somebody is knocking at the door of this doctor, right? We can use the expert system to say, oh, there is a 46% of chance that the guy is a smoker, right? Even though we did not see the guy yet, right? We have 4% of risk that he has cancer and 42% that he has dyspnea. Then, so these are prior probabilities. And then we can use a network for, let's say, simulation. So now let's suppose that he is in our office is saying, oh, okay, I'm a smoker, so we know that for sure, so we don't have any more uncertainty on smoker, so we're going to set 100% on smoker, yes. This will be propagated in the entire network, right? So now, given that he's a smoker, we have changed the probability distribution that he has bronchitis. The risk of cancer has been increased by 1%. Then also we have updated dyspnea and X-ray, right? And then, now let's suppose that he is telling us that he is suffering from dyspnea. Now we have used the network for, at the same time, simulation and diagnosis, because we have information here at the top level and here at the bottom, right? So we have now updated the criteria of cancer. This guy has 8% of risk to have cancer, given that he's a smoker and he's also suffering from dyspnea, right? So this is one of the main points of Bayesian network. There is no input or output nodes per se. Everything can be used as input or output. You know, when you are using a neural network or regression or something like that, you are defining nodes that will be used for input and nodes that will be used for output. You cannot just say, hey, what happens on my input if I change the level of my output, right? So this is not doable. Here, you have a holistic representation of your domain, and all the nodes can be used as input or outputs. Right? So now I'm just going to use real quick this example to show the difference between observational and causal inference, right? So let's suppose I'm using this network for trying to compute what is the effect of smoking on cancer, right? So the naive approach would consist in comparing smoker no with smoker yes with my network, right? So I have this network. So if I set smoker equal no, I can see that the risk of cancer is 2.8. If I set cancer equal yes, smoker equal yes, sorry, I can see that cancer is equal to 5.38. So I'm just comparing these two probabilities and say, okay, the risk of smoker is 2.6. So the impact of smoker is 2.6 on cancer, right? But indeed, this is not correct at all, because what we did here, by setting smoker to true, we are increasing the risk of cancer, right, by using this pink path. But we are also, by using this probabilistic inference, reducing our uncertainty on age, because in this model we have defined that the younger you are, the most likely you are a smoker. So if we observe that you are a smoker, we are going to infer that you are younger than the average population, right? And here you can see that the expected age is 40. And because we are reducing the age, we are reducing the risk of cancer. So we have what we call a confounding effect here. So we are not just measuring the effect of smoker here, but we are mixing the effect with the effect of age. And if I do reverse, if I set smoker to no, then I'm going to decrease the risk of cancer. But I'm increasing the expected age, that is now 57, and then increasing the risk of cancer. So here, there is no way to use that for computing the causal effect of smoker. Because we have a link here between these two guys. We have two causes for cancer, and unfortunately, we have a link between these two, right? Because this is not coming from a controlled experiment. So if we want to do a causal analysis on this network, we have just to fix this probability distribution. So we have just to indicate to the network that we want to compare smoker yes and smoker no with the exact same distribution for age, so which is more or less equivalent to deleting the link between age and smoker, right? And then now we have the causal effect of smoker on cancer, and it's not 2.6 or 2.8 as before, but 5.3, right? So now this is really the causal effect, okay? So I'm going to use now a second example in order to, so this example is more in the Q2, so where we have data, right? And we don't care about causality, but just we want to focus on the association, right? And this is an example coming from the S&P 500. So we have in this data set 6 years of historical data, and we have the day-over-day return by company, right? So we have more or less 500 companies. We have 1,500 days of observation in our data set, and we want to see the relationship between when Apple, for example, increased by 1%, what are the change on the other companies, right? So if we have this kind of naive approach just by computing the correlation between these companies, it will be a nightmare because we'll have a matrix made of 500 times 500. So this is not the good way to tackle this problem. But here, this is what we can discover in a few seconds just by loading the data set. We can learn a Bayesian network that will represent the main relationship between these day-over-day return by companies, right? So here this is still a Bayesian network, even though the representation is slightly different from the one I had before, just because we just have increased the quality of the representation by analyzing the network. So in this graph, you have the nodes of different sizes, right? and the size is proportional to the strength, to the force of the node, right? And the connection between the companies here, you see that the thickness is not the same for all the relationships. So the thicker a connection is, the stronger the probabilistic relationship is. So when you have a deterministic relationship between two nodes, at the end of the day, you are not losing information, right? But when you have a probabilistic information or relationship, it's like having a hole. So you are losing some information, right? So if you say that when it's true, the other one is true, but only with 90% of chance, so you are losing like 10%, or you have 10% of uncertainty, if you will. So here, the image of this graph is to consider that the relationship is a kind of pipe or hole, and we have a hole in the pipe that is directly, the size of this hole is proportional to the uncertainty. So if it's deterministic, there is no hole. We are not losing anything. If it's very uncertain, then we have a big hole. Right? And then you have to imagine that we are injecting water in this system, in these pipes, and then if there is no hole, the pressure is high, and then the thickness is big. And if there is lots of uncertainty, you are losing lots of water, and then there is no pressure in your pipe. Right? And then using this same image, the size of the node is proportional to the strength, as I said. So this is indeed like a balloon. So you have a balloon with connected pipes here. So the more pipes you have and the thicker these pipes are, the higher the pressure is in the balloon, and then the bigger the balloon will be. And then you can use this imagery just to think about if you were able to squeeze a node, what could be the information that will be propagated in your network, right? So for example, if I squeeze NRG here, I'm not going to change a lot of things. So I will probably change a little bit Williams, but that will be it. But if I squeeze progress energy incorporation, then this will have lots of impact on the other nodes. So the image is really that. So this is the amount of information contained in the node. So if I have information on progress energy, I'm going to reduce the uncertainty on these neighbors, right? Which is not the case with NRG, right? So this is the image. So here, what we can see is that just by using this data set without any expert knowledge, we were able to recover here. These are the relationship between the nodes that are, or the companies that are working in the field of energy, right? If I go there, I'm going to see that we have P&G connected with Colgate, with Johnson & Johnson, Kellogg's, Campbell, General Mills, and so on, Kimberly-Clark. So this is the ecosystem of Procter & Gamble, right? Here we have electronic companies with Cisco, Intel, Hewlett-Packard, and so on. So, and again, without any expert knowledge here. So this is what we call unsupervised learning. So given a set of particles, if you will, that has been described in a structured data set, we are able to create this graph, right? And then, so a few months ago, we have also added a third dimension, because the challenge sometimes when you have lots of nodes like that, so you have huge graph, it's quite difficult to analyze it, right? So this previous one, 2D mapping, is nice to understand, but sometimes it's better to have a third dimension to be able to untangle the nodes. And what we have just added a few weeks ago now is the possibility to go into your network. So you can use VR, virtual reality, with the Oculus here, and then you will be able to navigate in your network, right? So this is, for example, a way, so this is the S&P 500. So we have the network, and then with your Oculus, you can directly grab the nodes. You can use this, I don't remember the name of this apparatus, but you can use this for defining what is the metric you're going to use for defining the size of the nodes. You can use this for defining the color or the thickness of the links. So this is really a way to explore your model. Even though in that example, for example, I have more than 500 nodes. So this is kind of huge network, but then you will be able to explore this network without any problem, right? So I will let you see this a little bit. We can, given the number of nodes, we can search for a specific node. So here I'm searching for PNG, and then it will be highlighted in yellow, and I can navigate and grab the node and see what are the companies that are connected with PNG, right? So given that you are fully immersed in your network, this is increasing a lot your capacity to analyze the model you have learned, right? So this was an example of Q2, and I still have a few minutes, so I can really quick go through one or two additional examples. So you can also use these networks for what we call supervised learning. So this is when you do have a target node, right? So this is, for example, for people who have leukemia, we have a data set of these guys, so two types of leukemia, and we want to really use a gene expression level to be able to find what is the optimal set of genes that will allow us to reduce the uncertainty or to discriminate between the two types of leukemia. And in this example, we have more than 7,000 genes, and we have 72 patients, and we just want to find a way to identify quickly what are the genes that are useful for discriminating between the ALL and AML leukemia. So this means that we start with a network made of 7,000 dots, right? So one per gene, if you will, and we have here the target node, so which is a leukemia type, and we can directly use supervised learning to focus on this leukemia type and to identify what are the useful genes, and then very quickly we will be able to extract the set of useful genes to do this probabilistic characterization, right? So then we can evaluate the quality of the model. So these are classical tools where you can compute the log loss, you can compute the precision reliability of your model, and so on. You can also export SAS code or R code or Visual Basic code, so in order to be able to exploit this model on new patients. You can generate trees like that. So this is now for trying to interpret, to harvest the knowledge that has been encoded in your model. And then this is also something that can be used for troubleshooting, because it's a static troubleshooting tool in that case. And you can also publish your network on the web. So we do have, for example, a web simulator. So given the network you have learned, you can, in a few seconds, publish your model on the internet and then allow everybody to use your model for inference, right? So in that case, it would be for diagnosis, right? And this is here an example of adaptive questionnaire, which means that we are asking the questions that will reduce the most the information given the cost to get this information. So this is like really a troubleshooting tool, right? So this is here incrementally given the answer you are given, we are updating the priority and each time computing what is the best information to gather. So still a few seconds, or perhaps I'm going to stop here. Rose, what do you think? No feedback?
Yeah, I think we do have several questions, so if you want to just maybe summarize, and then I could go to the questions, or?
Okay. So here,
okay.
If
go ahead.
Do you want to go ahead, or?
Yeah, no, go ahead. Go ahead and maybe do a summarization, and then I'll ask you some questions.
So the idea was just to say that, so I show you the way to build Bayesian network by expertise. You can do that by using unsupervised learning. So when, as the S&P 500, when you don't have any target node, you can use that for supervised learning. When you do have a target node, you can also do data clustering. So for the segmentation of your customer, your patient. You can also do that for variable clustering, for trying to find groups of nodes that are, or dimensions indeed, that are strongly correlated and that probably form a factor, if you will. So it's a kind of factorial analysis, but slightly different from the classical one. And at the very end of the day, when you are mixing all of these approaches, you can do what we call the probabilistic structural equation models And this is something this is what P&G is using every day for the optimization of their 300 brands. So this is for finding the drivers for optimizing sales. So I think I'm gonna conclude on that. So.
Okay, thank you, Lionel. We have a lot of questions just coming in, so I'm going to just start picking some of the ones that I've seen. We'll be able to do a few. The first one is, are Bayesian network topologies static during inference, or do topologies change during inference?
So once you have learned your network, so the network is not changing, right? So you have your model, and when you do inference, the model is not changing. If you want to changing online, then you have to use an API for that. And then to implement, yes, a specific program that will update. So either update the probabilities, or perhaps on the flow you can update the structure. But this has to be done by using an API.
Okay, thank you. Next question is, how do you automatically learn the dependency between nodes?
For learning the dependency, indeed, we are using what we call a score-based approach, which means that this is a score that is based on information theory. And the main idea, so I don't have the time to explain exactly how this is working because this would last 4 hours, but the main idea is that we are using information theory, right? And we are assuming that each node, each bubble, if you will, it's like an agent, and given the priority distribution associated with this node, with this agent, we have uncertainty. So for example, if you have a uniform distribution, this is a worst case scenario because you don't know what state to pick, right? You don't know in which state you are. And then this corresponds to the maximum entropy, the maximum uncertainty. And the idea of learning a Bayesian network by using information theory is trying to find the connection between the nodes that will allow you to reduce the uncertainty of the entire system, right? So we are really trying to connect the nodes that are strongly correlated in order to reduce the uncertainty of the entire system. So this is from a technical point of view, we are using at Bayesian a score that is called the minimum description length, so the MDL score, coming from information theory.
Okay, thank you. And next question, how is this different from decision trees?
Well, there is not, well, the only common thing was the interpretation tree I've shown, because here this is, in a decision tree, you have an input and output. In that case here, we really have a holistic representation of the system, right? So as I said in the example with the medical, with the 3 diseases, bronchitis, cancer, and tuberculosis, all the nodes in this network can be used for as input or as output, right? So when you build a decision tree or probabilistic tree, you have a target in mind. So it will be only for supervised learning in that case, right? Here, there is no way with a tree to have a holistic representation of your domain. You cannot, for example, do what I've shown with S&P 500. You can probably do the same thing for at least have a competitive approach for the leukemia example I used, but not for either the medical example or the S&P 500 example.
Okay, thank you. Next question, what is the computational complexity of the Bayesian net inference? Are modern servers fast enough, or is there a performance bottleneck?
Here, so I heard that it was a complexity for the inference, because there are 2 types of complexity. There are the complexity for learning the network, right? That depends obviously on the number of nodes you have, or when I say number of nodes, indeed this is the number of columns in your structured data set, and also the number of observations, even though the most important dimension is the number of nodes. And then it also depends if you have missing values, because then you have to handle these missing values online, which, by the way, this is the most efficient way to handle missing values is still to use Bayesian network, because we can directly handle this missing value while we are learning, right? Because we can do inference to estimate what are the probability distribution of these missing values. So there is a first complexity for learning. So in that case, it depends, as I said, on the size of the data set you are going to use, and also on the complexity of what I would call the ground truth network that is behind, the one you are looking for. So sometimes, if you have lots of connection between the nodes, it will be more expensive to discover than if you just have a tree, right? And then there is another component for the complexity is for inference. So when you have your network, the cost for computing all these probabilities. And this is also depending on the complexity of the network. So again, if you just have a tree, so when I say tree, this means that you just have a network in which there is only one parent per node. So in that case, the inference is very efficient, right? But if you have a very complex network with lots of connections, then indeed here the complexity will increase. But I would say that usually we don't really have any problem with inference, even without using very big computers.
Okay, thank you, Lionel. I have a question about the stock market network. They ask, why are there no cycles? One might expect some cycles of impact by one company on another.
Yeah, it's a good question. Here we have this very nice layout just because we have used what we call the maximum weight spanning tree for learning the relationship between the nodes. So this is it was just to have a nice graph. If you indeed learn without any constraints, you will have more connections than the one I had. But here it's just for the presentation. I don't want to have a bag of nodes because then it's much more difficult to understand. So here this is just a network that focuses on the very strongest relationship between the nodes. And this is indeed the best also course of action to use if you want to do some variable clustering. Because at the end of the day, when you have this kind of graphs, you can use it for creating groups of companies, right? So for example, having in the same group P&G, Colgate, and Kellogg's, right? And when you are planning to do this kind of variable clustering, the best thing to do is to start with a network that is not too complex and that really focuses on the strongest relationships.
Okay, thank you. We have time for maybe one, maybe two, depending on the answers, more questions. So another one, a lot of questions are coming in right now, so let me just pick a couple. Can you use an ensemble of Bayesian networks for inference if there's uncertainty about the network structure?
Say it again?
Can you use an ensemble of Bayesian networks for inference if there's uncertainty about the network structure?
Indeed, this is doable. So this is not doable, well, because in our package, so we have a desktop application, so that comes with a classical utilization of Bayesian networks. So this is not doable in our package directly, but indeed, if you use, again, APIs, there is absolutely no problem for that. So you can indeed use an ensemble of Bayesian network to carry out the inference if you have some uncertainty about the structure.
Okay, next question is it possible to use Bayesian framework for deep learning networks?
There are some deep learning Bayesian networks, but well, this is not something we are doing because here, well, usually deep learning is more for neural networks. So indeed, this is, and we still want to have. You remember what I presented with the difference between the black box and the crystal box. So we still want to be able to challenge and to audit our model, and so this is the reason why we are still not doing deep learning for that reason. Even though when we are doing variable clustering and then creating a latent variable, we are creating an additional layer. So it's not deep. We are not creating lots of layers, but we are creating one hidden layer. So there is nothing that prevents to create more and more layer, but then this is not really implemented yet.
Okay. I think we have just one more time for one more question, and this is if we don't have the prior knowledge of the causal network structure, how can we learn the network structure among the variables?
So here, in that case, it depends. So if you don't have any causal knowledge, and if you want to learn a causal Bayesian network, this is indeed a challenge, right? But it really depends of the objective of your model. So are you going to use your data for learning a model that will show you the main connection between the nodes, and then you want to use it for computing probabilities, right? So in that case, you don't really need causal knowledge. But if you are planning to use your model for doing some kind of causal inference to compute causal effect or measuring the effect of something on your market, then indeed here you need to use causal knowledge. And in that case, yes, you have to think about what are the direction of the connection, right? So there is no way right now to be to discover automatically a causal Bayesian network, even though we have sometimes some insight about the direction of the links, but we cannot guarantee that this is indeed a causal link. So we always need to use expert knowledge for having what we call a causal Bayesian network.
Well, thank you, Lionel. I'm afraid we've run out of time today. There's many more questions that have come in. I'd like to thank Lionel again for his informative presentation and insightful answers to many questions, and also a special thanks to each of you for taking the time to participate today. This webinar was recorded and will be available online in a few days at webinar.acm.org. You can find announcements on upcoming webinars and other ACM activities at those two links that are on your screen. Also, please fill out our quick survey where you can suggest future topics or speakers, which you should see on your screen. So on behalf of the ACM, SIGAI, Lionel, and myself, Rose Paradis, thanks again for joining us. And I hope you'll join us again for our next webinar in February. And we also will be having one a month for the spring session. Please also take a few minutes to take the survey and look at the SIGAI web pages and join our group. This concludes the webinar.